we are going to go ahead and continue with our example 10.7. So we were finding our acceleration here, our rotational acceleration, and from that we want to find our tangential acceleration. So A sub t is equal to r alpha. Okay, and so let's go ahead and plug these numbers in. We have 0.20 radius, and our acceleration is negative 35 radians per second. So from that we will get negative 7 meters per second. Okay, and there we go. All right, so now we have our tangential acceleration, and we found that to be negative 7 meters per second. Now we need to find our tangential velocity, so v sub t. So we found this guy. We now need to find this one. So let me go to another page. V sub t is equal to r omega. So we need to find omega, and our rotational velocity at this point, or angular velocity, will be at time t equals 29 seconds. So we have to take that into account. Okay, so we have t equals 29 seconds now. So what we'll do is we'll use this equation again, because we do have alpha now, to solve for our omega at this point. So omega is going to be omega naught plus alpha t. Okay, so let's go ahead and do that. Omega is going to be equal to omega naught, which is our 10,050 radians per second. So 10,050 radians per second plus alpha, which is negative 35 radians per second squared, times our time, which is 29 seconds. Okay, so we can plug that into our calculator. Let's see, negative 35 times 29, add that to 1050, and I get 35 radians per second. Okay. All right. So now from that we can find our v sub t. So v sub t is going to be r, which is 0.2, times omega, which is 35, and I get that our tangential velocity is 7 meters per second. Okay. All right. So now let me go back, and now we can find our centripetal acceleration here, since we found that. Okay, so our centripetal acceleration, a sub c, is equal to vt squared over r. So we'll have 7 meters per second squared over our radius, which is 0.2 meters. Okay, so let's do that. 7 squared over 0.2, and we get 245, and this is in meters per second squared. Okay, so now we have our centripetal acceleration and our tangential acceleration. Okay, and using those two and our equation back here, okay, we can find our acceleration, our overall acceleration, total linear acceleration. Okay, so this will be acceleration of c squared plus acceleration of t squared. So our centripetal we found was 245 meters per second. And our tangential we found was -7 meters per second. Oh, squared. Whoops. Okay. So we can put that into our calculator. We will get, let's see, that guy squared plus 7 squared. And we get our acceleration is 245 meters per second squared. Okay. Now it asks us for also the direction of this motion, so let's go ahead and do that. We have tan inverse of our y component, or our tangential component, -7 over 245, tan inverse, -7 over 245. Let's see. We get an angle of -1.64 degrees. Okay. Okay, one thing to note is that my directional motion is negative, so my theta, sorry, I didn't even put my angle here, or actually I should call it like phi or something, that this angle is negative, okay? And the reason that matters is because it tells us what direction our total acceleration is going to be, okay? So, and this, I mean, this was really 245.099, I mean, but if I'm being picky. Okay, so if I were to draw this circle, okay, this is a lumpy circle, but bear with me. We have some sort of acceleration, centripetal acceleration, towards the center of the rotation, axis of rotation. We have our tangential acceleration, so a sub t and a sub c, okay. This negative tells us that our acceleration is going to be in this negative towards the center as well, okay? That's all that that negative means, is that it's going towards the axis of rotation, okay? All right, so now let's look at rotational kinetic energy. Okay, oh, whoops. We want to find this kinetic energy now in rotational form. So let's see, V sub t is related to omega r, right? So V sub t, I'm going to go ahead and make that equal to 1/2 m r omega squared. Okay, so this is going to be our kinetic energy. Oh, whoops, r omega, this whole thing squared. There we go. Okay, so from that comes this equation down here. So what we do is we go ahead and say that the total kinetic energy is going to be a summation over all of these energies. Okay, so I can say kinetic energy is equal to the sum of all the individual energies, right? And when we do that, we will go ahead and sum it over these masses. Okay, so we have 1/2 summation of these masses and whatever radius they are at. Okay, so I'm not going to go in depth with this other than stating that this is the result, okay, and then we'll use that result. Okay, From that, we do get this idea of moment of inertia, okay? And so what is moment of inertia? So inertia, where is it? Oh, okay. Sorry. Okay. It's summing over all of the masses and at what radius they are at. Okay, so taking this into account. So when we're looking at rotational versus translational motion, rotational, we will be taking our moment of inertia into account, versus in translational, we just have to take into account our mass. Okay, so we can now write our rotational kinetic energy as K equals 1/2 I omega squared, where I is the moment of inertia. Okay, note that the moment of inertia has units of kilograms, meters squared. Okay, just a quick note. Now, here's a problem-solving strategy for these types of problems. We first want to determine the energy, or that energy or work is involved in the rotation. Okay. Then determine the system of interest, make a sketch like we have done in the past. Analyze the situation to determine the types of work or energy involved. If there's no loss due to any kind of friction or any non-conservative forces, then we say that mechanical energy is conserved. So we can say that K sub I plus U sub I is equal to K sub F U sub F plus U sub F. Okay. And then solve for your unknowns, whatever unknowns are present. Okay. So let's do an example of this. And I may have too many slides on the inertia portion, but I tried to kind of mix it up. So this is example 10.9. It states a small rescue helicopter has 4 blades, each 4 meters long, and has a mass of 50 kilograms. The blades can be approximated as thin rods that rotate about one end of an axis parallel or perpendicular to their length. The helicopter has a total loaded mass of 1,000 kilograms. Okay. The first part says calculate the rotational kinetic energy in the blades when they rotate at 300 RPM. Okay, so we want to know kinetic energy. So kinetic energy, remember, is going to be 1/2 mv squared, or 1/2 I omega squared. Right? Yes. Okay. Wanted to make sure. So I, remember, is going to be the summation over each mass and its axes. So I just want to note that. Okay. So each mass M sub j is 50 kilograms. Each R sub j, is 4 meters. Okay, and there's 4 of them, so we can really just multiply whatever this result is by 4, right? Because it'll just be adding the same thing 4 times. So we should have 1/2 times 4 times mr squared. Okay, omega squared. So we have our omega that is given to us here, 300 rotations per minute. And we have our mass and our radius. Okay. So we can start by putting this into a proper form. So I'm going to multiply that by, that's rotation. It's rotation, there's 2 pi radians, and then minute, there's 1 minute 60 seconds. Okay, so 300 times 2 pi and divided by 60, that is 31.4. So we'll continue this in the next video.